Greetings and welcome to today's topic, which will be the output transformer. It's this device right here. It's present in every single guitar amp I've ever seen or worked on. It's also one of the most misunderstood of all the components in the amplifier. So let's try to sort that out a little bit today and see if we can't gain some insights. First, the purpose of the output transformer is to match the impedance between the output tubes and the speaker, which is Greek to a whole lot of people. But let's look at the situation in the amp and see if we can't see why this might be necessary. As you recall from that previous schematic, the output transformer exists between the output tubes and the speaker. Well, let's look at what's going on with the output tubes. The voltage, the plate voltage on output tubes is high, say around 400 volts. Okay, the speaker voltage, however, is much lower, ranging from like 1 or 2 volts up to maybe 20 volts. So it's much lower voltage on the speaker side than on the tube side. Current-wise, let's look at the speaker. It's running 1, 2, 3, sometimes 4 amps of current through a powerful speaker, whereas the tubes, those of you familiar with plate current know that it is in small fractions of an amp. Say 80 milliamps, which is 0.08 amps. Now compare 0.08 to 1.6, and you'll see there's a huge difference in current on the speaker side than on the output tube side. Now the way to resolve this is to put a transformer between the two, and we'll have a high impedance on the high voltage side, impedance ranging from like 2,500 to 8,000 ohms. And then on the speaker side, we'll have a very low impedance, small winding, which is like from 8 to 16 ohms. So in our drawing of the typical output transformer, we'll draw one down here with all sorts of windings on the primary side. We'll say it has 500 turns of copper wire, whereas on the speaker side, we just have 50 turns. So this gives us the high impedance side to face the tubes, the low impedance side to face the speaker. Which brings up a term to describe output transformers, and that is the winding ratio. In this case, we see there's 500 turns on the left, 50 turns on the right. I think this math is not too challenging. That's 500 to 50, or 10 to 1 winding ratio. Please keep this in mind. The winding ratio is what defines output transformers. In fact, you could say that the relationship between the primary and secondary values, this is the tube side, this is the speaker side, is determined by the winding ratio. Now let's accept the 10 to 1 ratio that we saw in the little diagram that I showed you a few seconds ago. Now I know all the math and numbers are real scary. Some of you feel free to kind of gloss over this and just look at the end conclusion. Those of you who are somewhat adept at math will find this to be fairly elementary. Let's look at the voltage that's going on with this output transformer that has a 10 to 1 ratio. I put it in the amp, and let's just say for ease of math that the output tubes in this particular amp operate at a plate voltage of 100 volts. Okay, now with the winding ratio of 10 to 1, the 100 volts in the primary will be stepped down to 10 volts in the secondary. You divide the primary voltage by the winding ratio, which was 10, and you get 10 volts. So far, so good, I hope. Next, we'll look at the plate current. Let's say it's 0.1 amps. That's fairly high, 100 milliamps in the primary side. Well, over here on the secondary side, you will multiply by, when you deal with current, multiply that times the winding ratio, and you end up with 1 amp in the voice coil of the speaker. Which brings us to the impedance value. Let's use Ohm's law over here. 10 volts divided by 1 amp gives us 10 ohms of impedance on the voice coil of the speaker. Now, using this formula, we can calculate what the primary impedance is. You take the secondary impedance times the winding ratio squared. That was 10 to 1, so we take 10 squared, that's 100. 10 times 100 gives us 1,000 ohms of impedance. Conversely, if we knew the primary impedance was 1,000 ohms, we'll divide it by the winding ratio squared, which is 100. 1,000 divided by 100 gives us 10 ohms in the voice coil of the speaker. Now let's take a look at a statement that befuddles a lot of people. The primary impedance reflects the secondary impedance. Now what upsets a lot of people is that when they have their output transformer, they assume that its performance will be constant, like a resistor or a capacitor. No matter what happens, it will do whatever the numbers on it imply. But here's what happens. If you connect the output transformer up to a 10 ohm speaker, the primary will have 1,000 ohms of impedance. But if you connect it to a 5 ohm speaker, all bets are off. Now the primary impedance is not 1,000, but it becomes 500 ohms because the primary impedance reflects or adjusts to whatever the secondary impedance is. Now generally we don't change our tube schematic and alter our output tubes. We change the speaker. So that's where I'm going to address the changes here. Now, one of the biggest questions asked that I see all the time is, can I use a 4 ohm speaker in an 8 ohm amp, or one that's used to 8 ohm speakers? Well, let's take a look at what happens, and then I think you can answer that for yourself. Now, up here in my example, I used a 10 ohm speaker. Down here, I'm going to use a 5 ohm speaker. Now, let's look at what happens when I use a 5 ohm speaker. Immediately, the primary impedance becomes 500 ohms, not 1,000. Let's look at the values that are going on within the amp. First of all, the plate voltage is going to stay the same, and the voice coil voltage is going to stay the same no matter what. So it's still 110, just like it was up here. But let's look at the current. When you use Ohm's law and you say, well, I've got 10 volts in my voice coil divided by the 5 ohms in the speaker, now instead of 1 amp flowing through my voice coil, I have 2 amps, double the current. Let's look at what's going on the primary side. When I have my 2 amps and I divide it by my winding ratio, I end up with 200 milliamps going through the primary side of the output transformer instead of 100. So by using a speaker with half the impedance, I am now flowing twice the current through my voice coil and twice the current through the primary winding of my output transformer. Can you see where this might cause a problem? Going down in impedance of speakers increases the current flow and increases the chance you're going to burn up the speaker or burn up the output transformer. Now let's look at what happens when I use a much higher resistance speaker. What if I go, instead of my 10 ohms, I go to a 20 ohm speaker? Well, I think you can sort of predict by now what's going to happen. First of all, the impedance of the primary is now going to reflect this, and it's times 100, the winding ratio squared. So now in my primary I have 2,000 ohms of impedance. Well, you know that's going to slow down the current flow. And sure enough, the current flow goes down to 50 milliamps in the primary. Not 100 with 10 ohms, not 200 with 5 ohms, but half, 500 milliamps. Over here in the voice coil, the current's going to go to half also. We don't have now 1 amp of current, which was what we wanted. We don't have 2 amps, which is way more than we wanted. We have about half what we want. So going to a higher impedance speaker will not damage your components. It's not going to burn up the speaker. It's not going to damage the output transformer. But as you can see, we're operating here on suboptimum current levels that are going to have a negative effect on tone and volume. So the best solution here is use the output transformer with the speaker impedance with which it was intended, and you will have the right reflected primary impedance for the output tubes. Your performance then will be regulated by 100 milliamps, which is correct for your output tubes, and 1 amp flowing through your voice coil. You're going to get great volume, great tone, great fidelity, everything's good. Down here, a chance of damaging components, and down here, greatly reduced tone and volume. Now, for all of you rolling your eyes and hating the math and hating all the numbers, then forget them. It doesn't matter. All you need to take away from this is, if I use a lower impedance speaker, I take a chance on damaging my speaker and damaging my output transformer. If I use a higher impedance speaker, I will probably have worse tone and lower volume than I should, and my amp will not sound as good as it should. A simple answer to a rather complex issue. For those of us who have bought output transformers from places like Hammond or Triode USA, you know that generally they'll tell you what the primary and secondary impedance are. They don't tell you the winding ratio, which would be very useful to know. So I will show you here a very easy method to find it out if you know these two values. This is the algebraic proof over here, which you can ignore. All you do is take the primary impedance, which is the big number, the secondary impedance, which is the smaller number, divide, and in this case we get 625, and then just take the square root of it. The square root of 625 is 25. The winding ratio for this transformer is 25:1. Now sometimes you'll encounter an output transformer that you got out of another amp and you have no idea what this impedance is or this. And there are ways to determine, and I'm going to demonstrate in a little experiment, how you can determine the winding ratio of any transformer. Now that brings us to this mysterious and rather large and bulky output transformer that I took out of an amp. I have no earthly idea what the winding ratio is, and therefore I have no idea what the primary impedance will be if I hook it to an 8 ohm speaker or a 4 ohm speaker. So let's figure that out. Now we'll determine the winding ratio of this unknown output transformer. And I'm going to give you a little tip here. If you can find on Craigslist anybody who's trying to virtually give away an old vacuum tube organ, go get it, because they have wonderful speakers, transformers. These are Hammond transformers, okay? Tubes, all kinds of wonderful components, and you can buy just about everything you want for like pennies on the dollar. So that's the tip for today. Now let's figure out this winding ratio. Okay, here's how I've hooked it up. First of all, I am using something called a Variac. What this is, you plug it into the wall at like 120 volts, and then as I crank this knob up, it puts out more and more alternating current from 0 up to 110 or maybe even 120 volts into whatever I have it connected to. In this case, I have connected it to the tube side of the output transformer. Recall that the tube side of the output transformer is the one that handles the high voltage, 300, 400, 500 plate volts. So we're going to hook our Variac to the opposite ends of the tube side winding. This over here is the center tap. This is what would go to the B+ in your circuit. I taped it off. I want to run through the full primary winding then of this transformer. Then I've connected to each of the Variac alligator clips over here to my AC voltmeter, where I can tell exactly how much voltage the Variac is sending into the tube side winding of the primary transformer. Then on the speaker side winding, I hooked up a AC voltmeter over here, and I have it set where it's 0 to 2.5 volts maximum deflection. Now, to keep the math easy, I'm going to turn up the Variac and send more and more voltage in here to the tube side of the transformer, and then monitor what comes out on the speaker side. And when I get to exactly 1 volt, 1 AC volt output, then when I look over here at the amount of voltage I put in, which will be probably anywhere from 20 to 40 volts, that will be the ratio. This to 1 ratio. If this reads 40 volts, then it's a 40 to 1 winding ratio. Now, let's start up and see what we get. Okay, Variac is on. And now I'm going to watch the output. And I'm going to crank the Variac up. Until I reach exactly 1.0 AC volts out on the speaker side, and then I look over here at the input side. It is 29.4. The winding ratio of this transformer is 29.4 to 1. Now that I've determined that the mystery output transformer has a 29.4 to 1 winding ratio, it gives me all sorts of information as to what type of amp I can use it in. These are the speaker impedances that I could pick: a 2 ohm, 4 ohm, 8 ohm, or 16 ohm speaker, and this is what the primary impedance would be with this speaker. The way I get these numbers over here is it's times the winding ratio squared. 29.4 squared is 864. You multiply and get the primary impedance values. Now let's pick one, the 6912 ohm primary impedance with the 8 ohm speaker, which is the most common speaker and probably the one that I would like to use. Let's take a look at this chart. Now, this chart came from the Sylvania Tube Handbook and then was verified through Hammond transformers. Look here and you'll see that remember I had 6912 ohms of primary impedance. It really looks like it's very close to this value, which would mean that this output transformer is ideal for a push-pull AB1 amp with 2 6L6 output tubes. Now, if the winding ratio had led to a reflected primary impedance of 8,000 ohms, I might want to use it in a 6V6 push-pull amp. If it were 4,500 ohms, then that transformer would have been great for a single-ended 6L6 amp. So you see how it works. Once you know the winding ratio and you know the impedance of the speaker you want to use, then you can go back and figure out what type of amp would work with the mystery output transformer and with the 8 ohm speaker that you've chosen. Thus we've seen there's 2 different ways to determine the winding ratio of a transformer. If we know what the primary and secondary impedance is, you simply divide the primary impedance by the secondary impedance, get the answer, and then take the square root of it, and that will give you the winding ratio. Or you can use the method I use with the Variac, where you pump in 1 volt of alternating current over here on the secondary side, and then measure what kind of output voltage you're getting on this side, and that will tell you what the winding ratio is. Now, some people might think, well, I'm just going to take my DC ohm meter and hook it across this terminal and this terminal, and I'll measure that 5,000 ohms, and then I'll hook my ohm meter across these 2 terminals, and I'm going to measure that 8 ohms. And I invite you to try, because it's one of life's great disappointments When your brand new shiny DC ohmmeter doesn't work well measuring resistances on transformers and coils. The reason is these values right here are in ohms of impedance, not ohms of resistance. There is a huge difference between impedance and resistance, and it's a difference that not all that many people understand, so let's address it. This might be a good time to address the difference between resistance and impedance. I think most people just lump the two terms together and figure impedance is some fancy way to describe resistance, and really that's not the case. When we measure resistance, we use an ohmmeter, and what we end up with is strictly a measurement of the circuit or component resistance to direct current. That's fine, except that in music amplifiers, the music signal itself is not direct current, but is alternating current. Now, most of us think of alternating current as something that lurks in the wall socket and is useful to power hair dryers. But the circuit sees any type of signal that rises and falls, just like the music signal does. It perceives it as being alternating current, and it treats it very differently than it does direct current. If we were to measure, say, a coil, and this is true of coils, such as filter chokes, also voice coils and speakers, and transformers. If we measure the coil in any of those devices with a ohmmeter, we'll find the direct current resistance. And say in this particular coil we measure it and it's exactly 8 ohms. But if alternating current tries to pass through exactly the same coil, it will encounter not just the 8 ohms of resistance due to the coil itself, but because it's alternating current, it's going to cause a field to be set up here in the coil that will further hinder the passage of the alternating current. In fact, it will hinder it to the point that the alternating current will see a resistance that's more like 10 ohms to pass through what direct current saw as an 8 ohm coil. Now this 2 ohms of increased resistance that we encounter with alternating current is called reactance. It's how the coil reacted to the alternating current. And the higher total resistance that the alternating current sees as it passes through this coil is called impedance. It generally amounts to about 1.25 times the DC resistance. This is why when you test the voice coil on your new 8 ohm speaker and you hook up your ohmmeter, it reads more like 6.25 or 6.5 ohms. And you're thinking to yourself, they must have made a mistake. Well, no. When AC passes through that same voice coil, and AC is exactly what will pass through it because the music signal you're going to send to the speaker is alternating current, it will encounter an impedance of not just the 6.5 ohms you measured, but a total of 8 ohms. So, just a quick review. I think the terms explain themselves pretty well. The coils react to AC, that's reactance. It's extra hindrance to the passage of alternating current through the coil or transformer. And when we lump together the reactance to the just basic resistance of the component, we end up with a higher overall resistance that we call impedance. Impedance is the hindrance that a device or circuit presents to alternating current. Well, that about does it for this topic. And this was not ground level. I'd say this is probably a little more intermediate level, but we covered this mysterious device right here. I think now we understand its purpose. We understand what a winding ratio is. We understand the difference between impedance and resistance. And we now know several ways to determine the nature of mystery output transformers and output transformers that we buy on the internet. So I think we've accomplished quite a bit. Well, I apologize for all the math and for the fact that some of these concepts are a little abstract. But I think if you want to learn how to swim, sometimes there's nothing like just getting thrown in the pool. So let's dry off and move on. And I really appreciate your time and your interest. I hope you'll subscribe if you haven't. And I hope that you stay tuned for future videos. Thanks so much.